Hello, and in this video we're going to be looking at the first part of the properties of logarithms. We're going to be using these to solve equations in the future, but we're going to try to work through some of these that are given in your outlines for section 5.5 and 5.6. So the first properties we're going to use are the logarithm of 1 property. So anytime we have a logarithm of 1, that's going to equal 0. So the log of 1 is always equal to 0. And then the other logarithm that's going to be a common one is if the bases are the same. Log with the same bases. Base here and the base here is the same. That's going to be 1. So I have some examples here of those situations that are right off the bat here. So anything with the log of 1, doesn't matter what the base is, it's going to be 0. So if we're looking down my examples here, we can see that my first example has a log of 1. It's actually in base 10, right? So this log is in base 10, but it doesn't really matter the base. It's always going to be 0. So down here in example 3, same thing. Base e, but that's also going to be 0. And in here in example 5, that's going to be also 0. So all of these logs, doesn't matter what the base is. Base 10, base e, base 3, all of them are going to be 0. That's a logarithm of 1. That's a definition. Because 10 to the 0 power is 1. E to the 0 power is 1. 3 to the 0 power is 1. So using the exponential conversion, we can see that that's true. Now in this case, log with the same base, so this one doesn't have a base written, but since it's a common logarithm, it has a base 10, so we can see now if we wrote that there that these are going to be the same, so this is going to be 1. Same thing here in example 4. The bases are the same, even though it's not written here. Bases are the same, so that's also going to be 1. E and E, both a natural logarithm. And then in example 6 here, you can see that they actually are written the same, so this is 1. So anytime we have the same bases, we're going to get 1. Anytime we have the logarithm of 1, we're going to get 0. So those are the first two properties you should know, and they should help you simplify quite a few problems later on. Alright, another two properties here is if the bases are the same but we have an exponent there, then what we're doing is we're doing an inverse. So we're going to end up with just the x value. So that's the inverse functions. We're going to use log base a, and base a to the x power are going to be inverse functions, and they're going to basically reduce each other out and just leave you the value of x. And same thing here. A to a power is the inverse of log base a to the power to the number, so that's going to leave you x as well. So these are inverse functions of one another, and they're applying the inverse function. We're going to take the log of an exponent, exponent of a log. So anytime that occurs, we're just going to get the value of x. In this case, the exponent, in this case, the log value. Alright, so on my first example here, I have 10 to the 4th. So the bases are the same. 10 to the 4th, so this is just going to be 4. It's going to be the exponent. This one right here, the second example, we have to write this as an exponent in order for us to write this, to figure this out. This is log base 10 of 10 to the 1/3 power because of the cube root. Cube root is 1/3, so our answer to this is 1/3. Same thing's going to happen here in this log base 10, common logarithm, log base 10. We have to write this number as a power of 10. So in this case, it's 10 squared, but it's 1 over 10 squared. So this is 1 over 10 squared, which is 10 to the negative 2nd power. So the answer to this is -2, because that's the exponent that gives us the 1 over 100. When we raise 10 to the negative 2 power, we get 1 over 100. Alright, this one is a tricky question here. We're not raising the power until after we take the logarithm. So the logarithm here is actually, this is the previous one, which is this example right here. Log base a of a. So this part right here is log base 10 of 10. So this is going to be 1 to the third power, which is 1. So it's a little bit tricky in that they didn't put the third power on the value, they put the third power on the whole logarithm. All right, and logarithms, we know that the values of logarithms have to be positive. So you need to know that you can't take the log of negative numbers. So there's no solution here, no answer to this problem. If we try to do that, the logarithm has a vertical asymptote at 0 and then it goes to the right on the graph. So there isn't any graph on the negative side. All right, and this is a combination of the problem we had in example 4 and the problem we had in example 1. So this part right here is going to be 5 because of the exponent, and this part here is going to be 1 to the 5th power, which is going to be 6 total for this problem. So those are my solutions to these examples. All right, so that's using the inverses. So that's a tricky one. You have to look and see if they have a to the logarithm or we have a log to the base. On all of these we had a to the logarithm, or log to the base, sorry. So the other versions we could have here is a to the log base 4. So you could also have some of those. So why don't we try a couple of those here. We'll move this down and we'll just make up a few problems with that type. Move this stuff down. And then we'll have one more problem, one or two more examples here of the other type here. We don't have an example of the base. So let's do 3 to the log. So in this example, we're going to do 3 log base 3 of 4 to the x power, 4x. So in this case, this base and this base are the same. We're doing a exponential to a logarithmic one, so we're just going to end up with 4x here because they're inverse functions. So you didn't see one like that here where we have a base first. Here we had the logarithms first and then the base. Here we have the base then the logarithm. We still get the same type of problem though. We're going to get the value that's up here in the logarithm as our solution. Okay? So another example, 10 to the log of 5x plus 1. So in this case, we don't see the base here, but it is base 10. So in this example, we would still get 5x plus 1 as our solution. These are our inverse functions. And let's look at one more example with a natural log. So if I had e, because that's my base here, e to the ln of 2x. Then these are our inverse functions, so this is just going to be 2x. So any of those types, those are like the reverse, that's these values up here of this version. All right, let's move on to the last part of this video, and that's change of base formula. So this is the change of base formula. It allows us to use our calculator to evaluate logarithms that are not pre-programmed in here. So we have base 10 logarithms here on this key. So we can take the log base 10 of something, and we can take the natural log of some value right here, but we can't take and figure this value out without a change of base formula. We can estimate what this is, Now I could estimate what this is. 4 to the, by just using some estimation skills, I know that 4 to the second power is 16, and 4 to the third power is 64. And since 27 is in between these two values, my answer is going to be between 2 and 3. So I know it's between 2 and 3, and since 27 is closer to 16, it's going to be probably less than 2.5 also. But we actually have a change of base formula that allows us to use our calculator to compute the value from the calculator. Now the change of base can be used with log base 10, or it could be used with ln. In this case we could also use ln of the m and over ln of a. So we can do this in two different ways. We can use either key on our calculator and we can find the value. So what I'm saying here is that this could be changed using this rule as log of 27 divided by log of 4. Or it could be ln of 27 over ln of 4. We should get the same answer. We change the base to one of the known ones. We should be able to get the same answer. Log 27 divided by log 4 is going to be approximately, so we're getting an approximation here. So we're approximately 2.377 to 3 decimal places. And if we did this on our other calculator, or our other, using the other logarithm here, we should get the same answer. ln of 27 divided by ln of 4. So I should get the same answer here, and my calculator verifies that it's still the same number, 2.377. So we use a change of base when we're trying to evaluate something where we know that it's between two values, but we can't figure out exactly what it is. And this allows us to do that.